out there, far beyond anything we can ever reach. Gravity has been working longer than memory. It has gathered matter, bent space, and quietly built structures so large that even light takes billions of years just to report back. Somewhere in that darkness sits an object whose presence is felt more than it is seen, not because it announces itself, but because everything around it must respond. This is not a story about spectacle. It is a story about scale, patience, and the quiet consequences of gravity doing what it does best. At extreme scales, words like whole begin to fail us. Phoenix A is not an empty void punched into space, nor a tunnel leading somewhere else. It is a region where space-time itself has collapsed under its own weight, where gravity no longer behaves like a pull, but like an overwhelming condition that everything nearby must obey. In this region, geometry is distorted beyond anything we experience locally. Space bends inward so steeply that all possible paths curve toward a single fate. Time does not simply pass there, it flows inward, dragged along with matter and light toward a boundary we call the event horizon. Beyond that boundary, escape ceases to be a meaningful concept. I find it helpful to think of Phoenix A not as an object, but as a process, a continuing collapse that never quite finishes, endlessly consuming energy and reshaping the space around it. At this scale, gravity does not sit inside the universe. It defines the local universe. Around Phoenix A, entire galaxies orbit like debris, caught in a slow, cosmic storm. Their motions are not chaotic, but they are not gentle either. Everything in the Phoenix cluster feels the influence of this central mass, from the largest galaxies to the thin gas drifting between them. From the core, colossal jets of plasma erupt outward at nearly the speed of light. These jets do not flicker or wander randomly. They punch through the surrounding intergalactic medium with astonishing focus, carving enormous cavities that remain visible across millions of light years. The scars they leave behind are written directly into the structure of the cluster. Tonight, sitting with that image, it becomes hard to think of Phoenix A as passive. It is not simply sitting at the center, quietly pulling things in. It is actively shaping its environment, injecting energy, rearranging matter, and leaving marks that persist long after the jets themselves have faded. The cavities formed by these jets are not small features. Each one is vast enough to swallow entire galaxies like our own. Hot gas is displaced, pushed outward, and forced into new configurations by the black hole's activity, even at distances that dwarf our imagination. Phoenix A continues to make its presence known. Despite this violence, the Phoenix cluster is anything but dead. Light fills the region, emitted by superheated gas, newborn stars, and energized particles spiraling through magnetic fields. The darkness at the center does not erase illumination. It reorganizes it. There is something deeply counterintuitive about that. A structure defined by collapse ends up creating some of the brightest phenomena in the universe. The same gravity that traps light also fuels the processes that generate it. Destruction and creation appear tangled together in ways that resist simple labels. The black hole's influence extends far beyond its immediate boundary. Energy released as matter spirals inward is redistributed throughout the cluster, heating, gas, and driving motion on immense scales. Phoenix A is not isolated. It is connected to everything around it through gravity and feedback. I think this is the moment where the usual mental picture of black holes breaks down completely. The popular image suggests isolation, silence, and emptiness. Phoenix A reveals something else entirely: interaction, structure, and ongoing transformation. Nothing about this system feels static. Gas flows inward along filaments that twist through the cluster like cosmic rivers. Energy flows outward through jets and radiation, shaping cavities and compressing matter elsewhere. The cluster breathes, expands, cools, and rearranges itself in response. Even the notion of surface loses meaning here. There is no solid boundary, no edge you could point to and say, this is where the black hole begins. The event horizon marks a limit of information, not of material substance. It is a mathematical threshold, not a physical wall. Light approaching that boundary does not bounce or shatter. It simply curves inward, following the geometry of spacetime until it can no longer return. Time follows the same fate, stretched and redirected until its outward flow effectively stops for distant observers. From far away, Phoenix A appears calm, even elegant. From nearby, it would be anything but. Tidal forces would stretch objects beyond recognition, tearing atoms apart long before the horizon is reached. Reality itself becomes unstable under gravity. This intense, what stands out most, at least to me, is how complete the black hole's influence feels. Nothing nearby is unaffected. Motion, structure, temperature, and even the flow of time are reorganized by its presence. Phoenix A does not merely exist within the cluster, it defines it. At this point, the scale alone is overwhelming, a mass exceeding 100 billion suns, compressed into a region smaller than our solar system, reshaping galaxies across millions of light years. It is difficult to hold all of that in mind at once without something slipping away. And yet, even this description only captures part of the story, because while Phoenix A consumes matter relentlessly, the space around it tells a far more complicated tale. One where collapse does not simply extinguish activity, but sets the stage for something unexpected. Just beyond the reach of this darkness, something else is happening. Something that should not, according to our simplest models, be happening at all. And that is where the paradox truly begins. Just beyond the immediate influence of Phoenix A, the universe does something unexpected. Instead of falling quiet, the surrounding region is alive with activity. Stars are forming at a staggering rate, igniting by the hundreds each year in what astronomers call a starburst. Compared to the calm, steady pace of star formation in the Milky Way, this region feels almost frantic. This is where the paradox sharpens. According to our standard understanding, black holes like Phoenix A should suppress this kind of activity. Their energy output heats surrounding gas, preventing it from cooling and collapsing into new stars. In astrophysics, black holes are often described as regulators, cosmic brakes that slow down growth. Phoenix A refuses to play that role. Despite its enormous appetite, the Phoenix cluster is undergoing one of the most intense star-forming episodes ever observed. The same reservoir of gas that feeds the black hole is also fueling the birth of new suns. Instead of quenching the fire, the system appears to be sustaining it, balancing destruction and creation in a way that defies simple explanation. I think this is one of those moments where the universe quietly reminds us not to trust tidy stories. The rules we extract from averages and simplified systems begin to wobble when pushed to extremes. Phoenix A lives in a regime where feedback does not behave politely, and outcomes do not follow expectations. Some astronomers suspect that the black hole's jets are not dispersing gas at all, but compressing it. As the jets plow through the cluster, they may be squeezing dense filaments of gas, triggering star formation rather than preventing it. In this view, violence becomes a catalyst rather than a deterrent. Others argue that we may be witnessing a brief and unstable phase. Perhaps this balance cannot last. Perhaps the system will eventually settle into a quieter state, with star formation fading as the black hole asserts control. If that is the case, then what we are seeing now is a snapshot, a rare moment frozen in cosmic time. Both explanations carry weight, and neither fully resolves the puzzle. The observations are real, but the mechanisms remain uncertain. Phoenix A exposes a gap between theory and reality that has not yet been closed. What stands out is not just the scale of the starburst, but its location. It unfolds dangerously close to one of the most destructive environments in the universe. Stars are forming in the shadow of a gravitational giant that could in principle, tear them apart. That tension feels important. Creation is not happening in spite of destruction. But alongside it, the same gravitational engine driving collapse is also shaping the conditions that allow new structure to emerge. Cause and effect blur together at this scale. I find myself returning to that idea again and again. We tend to separate processes into opposites: growth versus decay, creation versus annihilation. Phoenix A suggests those divisions may be conveniences rather than truths. The universe seems comfortable letting them overlap. The Phoenix cluster does not appear confused by this contradiction. Gas flows, stars ignite, jets erupt, and gravity continues its slow, inexorable work. The system operates as a whole, not as a set of competing forces. In that sense, Phoenix A is not an exception to cosmic rules. It may be revealing how incomplete our rules still are. Extreme environments expose assumptions we didn't realize we were making. The paradox at the heart of the Phoenix cluster is not just a curiosity. It forces a re-evaluation of how black holes interact with their surroundings, and how galaxies grow under their influence. If the most massive black holes can sometimes encourage star formation rather than suppress it, then our picture of cosmic evolution must become more flexible. Tonight, sitting with this contradiction, it becomes clear that Phoenix A is not simply a destroyer at the center of a dying system. It is embedded in a living, dynamic environment, one where gravity fuels both endings and beginnings at the same time. That realization shifts the question. Instead of asking why Phoenix A is so violent, we are left asking how such violence can coexist with such abundance. We need to step back and look more carefully at the nature of mass itself, and what gravity becomes when it reaches truly extreme scales. When we talk about Phoenix A, everything eventually circles back to mass. Not mass as a number on a page, but mass as a condition that reshapes reality around it. Even our sun, vast and ancient as it is, already dominates its surroundings, containing almost all the mass of the solar system. Multiply that influence by 100 billion, and the familiar intuition simply collapses. Phoenix A packs more than 100 billion solar masses into a region smaller than our own solar system. At that density, gravity stops behaving like a force that pulls things together and starts behaving like an absolute rule. Space itself bends under the weight, and motion becomes constrained by geometry rather than choice. Near this object, the idea of a surface no longer applies. There is no solid boundary, no edge you could touch. Instead, there is a singularity, a point where density becomes so extreme that our equations lose their grip. Around it lies the event horizon, an invisible threshold where escape ceases to have meaning. I find this boundary strangely unsettling, not because it is violent, but because it is final. Once crossed, information cannot return. Light curves inward. Time follows the same path. From the outside, everything appears to slow, stretch, and fade, frozen just short of disappearance. Gravity here is not simply strong. It is total. Every possible trajectory leads inward. Even standing still becomes impossible, because still has no definition when space-time itself is falling. Phoenix A does not sit inside the universe as we experience it. Locally, it replaces the rules. Yet this collapse is not loud. There is no explosion at the horizon, no dramatic tearing visible from afar. The black hole reveals itself only through consequences, distorted orbits, accelerated matter, and energy released as gravity does its work. That quiet dominance is what makes Phoenix A so difficult to grasp. Its power is not expressed through motion alone, but through constraint. It decides what paths are allowed and which are forbidden, long before anything actually falls inside. At this scale, gravity is no longer one interaction among many. It becomes the background against which all other processes unfold. Chemistry, radiation, and motion all submit to the curvature imposed by mass. Holding this in mind, the paradox from before begins to sharpen rather than soften. If gravity here is so overwhelming, if collapse is so complete, then the persistence of light and star formation nearby feels even more surprising. The conditions seem stacked entirely in favor of destruction. And yet, Phoenix A does not erase structure. It organizes it. The same mass that warps space-time also channels matter into flows and filaments. Gas does not simply vanish. It spirals, heats, cools, and redistributes its energy before ever reaching the horizon. Gravity sets the stage, but it does not dictate a single outcome. This is where mass stops being just a quantity and starts acting like an architect. The shape of spacetime determines how matter behaves, where energy accumulates, and how large-scale structures emerge. I think this is the moment where Phoenix A stops feeling like an object and starts feeling like a system, a deep well in reality. Yes, but also a generator of motion, heat, and light far beyond its core. Understanding that shift is essential, because the brilliance we see from the Phoenix cluster does not come from the black hole itself. It comes from what happens as matter struggles, briefly and violently, against gravity before finally yielding. And that struggle is written most clearly in the light that escapes. The light we associate with Phoenix A does not come from the black hole itself. Nothing escapes from inside the event horizon, and no glow marks the singularity beneath. What we see instead is the violence of approach, matter caught in the final struggle before surrendering to gravity. Gas and dust falling toward Phoenix, a do not plunge straight in. They spiral, forming a vast accretion disk that flattens and accelerates as it tightens its orbit. Friction, compression, and magnetic turbulence heat this material to billions of degrees, forcing it to radiate enormous amounts of energy. In these final moments, matter becomes brighter than entire galaxies. I find this deeply ironic. The darkest objects in the universe reveal themselves through light. The closer material gets to annihilation, the more intensely it announces its presence. Gravity does not simply swallow energy here, it transforms it. That radiation does not stay local. It floods the Phoenix cluster, bathing surrounding gas in X-rays, radio waves, and infrared light. The black hole's feeding process becomes a broadcast, carrying information about extreme physics across vast distances. Every photon released is a record of matter losing its battle with gravity. Those photons travel for nearly 6 billion years before reaching us. When our telescopes collect them, we are not seeing Phoenix A as it is now, but as it was when the universe was younger, denser, and less settled. The light is a time capsule, preserving a moment from an era we can never visit. There is something humbling about that delay. Entire civilizations could rise and vanish on Earth while those photons are still crossing intergalactic space. By the time they arrive, the system that created them may already have changed beyond recognition, yet the message remains readable. From that light alone, astronomers reconstruct mass, motion, temperature, and structure. The accretion disk becomes a laboratory, allowing us to infer conditions that can never be reproduced locally. Phoenix A teaches without ever being approached. The energy released by accretion does more than illuminate. It reshapes the cluster through feedback. Radiation heats gas, altering how it moves and how easily it can cool. Jets channel energy outward, redistributing matter on scales that dwarf individual galaxies. Feedback is often described as a regulating mechanism. In many systems, it prevents runaway growth by keeping gas too hot to collapse. That expectation makes the Phoenix cluster even more puzzling. Despite the intense radiation pouring from its core, star formation nearby remains furious. The accretion disk should, by all rights, be hostile to creation. Instead, its energy seems to coexist with it. The same process that strips matter down and consumes it also seeds motion and structure elsewhere in the cluster. I think this is where the usual narrative of black holes as purely destructive entities begins to feel incomplete. Phoenix A does not simply end stories. It redirects them. Energy released in one place reorganizes matter in another, linking collapse and creation across vast distances. Light becomes the connective tissue. It carries energy outward, interacts with gas, and leaves behind patterns that shape future evolution. The black hole's influence is not confined to its immediate surroundings. It propagates, lingers, and accumulates. Every cavity carved by jets, every heated filament of gas, and every newborn star nearby bears the imprint of this feedback. Phoenix A feeds, but it also communicates. Its activity writes structure into the cluster rather than erasing it. What stands out most is how efficient this process is. Few phenomena convert mass into energy as effectively as accretion onto a black hole. A small amount of infalling material can release power on a scale that rivals the combined output of millions of stars. That efficiency makes Phoenix A impossible to ignore, even across billions of light years. Its presence is unmistakable. It dominates the cluster's energy budget, shaping its evolution through light alone. From this perspective, the Phoenix cluster becomes more than a collection of galaxies. It becomes a system governed by feedback loops, where gravity, radiation, and matter continuously influence one another. Phoenix A sits at the center, not as a silent sink, but as an active participant. The brightness we observe is not an accident. It is the visible signature of gravity doing work at its limits. And that work, paradoxically, sustains motion and complexity rather than extinguishing them. That tension between consumption and illumination sets the stage for an even deeper problem. If Phoenix A can radiate so intensely, feed so continuously, and still support activity around it, then a far more uncomfortable question begins to emerge. How did something this large ever form in the first place? Once that question appears, it refuses to go away. Phoenix A is not just extreme in its behavior, but in its very existence. According to our current understanding, black holes should grow slowly, patiently, over billions of years. They begin small, anchored at the hearts of young galaxies, and gain mass by feeding on gas, dust, and the occasional star that wanders too close. In this picture, even the largest black holes we know make sense. The one at the center of our own Milky Way, Sagittarius A*, weighs a few million times the mass of the Sun. Others reach into the billions. Massive. Yes, but still within the limits set by cosmic time and available fuel. Phoenix A does not fit that story. With a mass approaching 100 billion suns, it is simply too large, too heavy, and, perhaps most troubling of all, too early. The universe has not existed long enough, at least on paper, for a black hole to grow that massive through ordinary feeding alone. Even under ideal conditions, the math refuses to cooperate. I remember feeling a quiet sense of unease the first time I saw those numbers lined up. Not disbelief, exactly, but the recognition that something fundamental was being stretched past its limits. The models weren't slightly off. they were dramatically inadequate. Accretion has a speed limit. As a black hole feeds, radiation pushes back against incoming matter, slowing the process. This natural break prevents runaway growth. It keeps black holes large, but not absurdly so. Phoenix A seems to have ignored that constraint entirely. Simulations can be pushed, assumptions relaxed, efficiencies maximized. Even then, the timelines fall short. There simply isn't enough time in the history of the universe for Phoenix A to reach its current mass by conventional means. Something in the story is missing. This is not a minor discrepancy. It challenges the sequence we rely on to explain how structure forms in the universe. If Phoenix A exists, then either our models of black hole growth are incomplete, or the early universe behaved in ways we do not yet understand. The problem becomes sharper when we consider the environment. Feeding at this scale requires an enormous and sustained supply of gas. That gas should have been exhausted long ago, heated and dispersed by the very feedback Phoenix A produces. And yet, the black hole continues to feed. Every attempt to explain its size leads back to the same conclusion. Phoenix A did not grow quietly in the background. Its formation must have involved extreme conditions, rapid processes, or events that no longer occur in the modern universe. I think this is the moment where Phoenix A stops being an object of study and becomes a test, a stress point in our understanding. It forces theories to reveal where they break under pressure. The growth problem does not tell us what happened. It tells us that whatever did happen lies outside the comfortable boundaries of familiar physics. Phoenix A is too big to ignore, and too real to explain away. If ordinary growth cannot account for it, then the only option left is to imagine extraordinary origins, scenarios that reach back into the universe's most violent youth, when gravity may have operated under fewer constraints and matter behaved very differently. That possibility opens the door to ideas that feel almost speculative, but may be unavoidable. To understand Phoenix A at all, we may have to abandon the assumption that it formed the way most black holes do. And that brings us to the question of how something so vast could have been born in the first place. When ordinary growth fails to explain something, the mind is forced to wander further back in time. For Phoenix A, that journey leads to an era when the universe itself was younger, hotter, and far less orderly than it is now. The question is no longer how it grew, but how it might have begun. One possibility is direct collapse. Instead of forming from the death of a single massive star, Phoenix A may have emerged from the sudden collapse of an enormous cloud of primordial gas. Not thousands of suns, but millions, perhaps more, falling inward in one catastrophic event. In such an environment, there would be no time for stars to form first, no gradual buildup, just gravity acting without interruption. I find this idea unsettling in a quiet way. It suggests a universe capable of skipping steps, of jumping straight to extremes without passing through familiar stages. Structure would not gently assemble, but appear fully formed, heavy and dominant, almost from the beginning. Another explanation reaches for mergers. Galaxies collide frequently over cosmic time, and each collision brings their central black holes closer together. Over billions of years, these black holes can merge, combining their masses into something larger. In principle, repeated mergers could build a giant, but even this path struggles to reach the scale of Phoenix A. Too many mergers would be required, happening too quickly, in an environment already hostile to sustained growth. The arithmetic still feels strained, as though the universe would need to cooperate unusually well to make it work. That leaves a more uncomfortable possibility. Phoenix A may be a relic of conditions that no longer exist, a survivor from a phase of cosmic history when gravity behaved more freely, when gas was abundant and structure formed at breakneck speed. If that is true, then Phoenix A is not just massive, it is ancient in a deeper sense. In astrophysics, we like continuity. We prefer processes that scale smoothly from the small to the large, from the local to the cosmic. Phoenix A disrupts that comfort. Its existence hints at a universe that once operated under different rules, or at least under rules we have not yet learned to describe. This is where the language begins to fail slightly. We can propose scenarios, outline mechanisms, and test simulations, but none feel entirely sufficient. Each explanation accounts for part of the story, but not the whole. I think this is why Phoenix A feels so compelling. It refuses to settle into a single narrative. It carries traces of collapse, merger, and primordial chaos all at once, as though the universe layered multiple histories into a single object. What matters is not which explanation wins, but what their necessity reveals. Our current picture of black hole formation is incomplete. Phoenix A sits just beyond its edge, visible but not fully reachable, and once that boundary is crossed, a deeper shift begins to take place. Because if Phoenix A formed early and grew fast, then its role in shaping its surroundings may have been far more fundamental than we once believed. The black hole may not have been a passenger inside the Phoenix cluster. For a long time, the relationship between galaxies and black holes felt simple. Galaxies formed first, rich with gas and stars, and somewhere later, a black hole would grow quietly at the center. It was a supporting character, influential but secondary, shaped by the galaxy that hosted it. Phoenix A turns that story inside out. Evidence from the Phoenix cluster suggests that the black hole may have come first, or at least grown powerful enough early on to dictate what followed. Its gravity appears to control how gas moves, where it cools, and when it collapses into stars. Instead of reacting to the galaxy, Phoenix A seems to be writing the blueprint. The clearest signs of this are the enormous cavities carved into the surrounding plasma. Radio observations reveal vast, hollow regions blown open by jets launched from the black hole millions of years ago. Each cavity is large enough to swallow the Milky Way whole, leaving behind scars that stretch across intergalactic space. I find these cavities strangely beautiful, not because they are empty, but because they show absence as evidence. We do not see the jets themselves anymore, only the space they displaced, like footprints left in fog. Gravity announces itself not by what it shows, but by what it removes. As these cavities expand, they push hot gas outward, redistributing energy throughout the cluster. Eventually, that displaced gas cools and rains back toward the center. In doing so, it feeds both the black hole and the surrounding starburst, restarting the cycle once again. This feedback loop feels almost biological. Inhale, exhale. Expansion followed by collapse. The Phoenix cluster breathes on timescales measured in millions of years. With Phoenix A acting as its beating heart, structure emerges not despite this rhythm, but because of it. The black hole does not merely consume matter at the center. It sculpts the environment far beyond its reach. Jets define channels. Cavities regulate temperature. Gravity sets the pace at which gas can settle and ignite. Entire galaxies respond to this invisible architecture. This realization quietly shifts perspective. If black holes shape galaxies so profoundly, then many features we attribute to galactic evolution may actually be consequences of gravitational dominance at their cores. Stars, spiral arms. Even the distribution of matter may trace paths laid down by something fundamentally dark. I think this is why Phoenix A feels less like a monster and more like a framework. It is not chaotic in the human sense. Its influence is structured, repetitive, and strangely orderly. Destruction follows patterns. Creation follows those patterns in turn. In the Phoenix cluster, gravity is not just pulling inward, it is organizing outward, Matter flows according to gradients set long ago, responding to an engine that has been operating for billions of years without pause. This makes the paradox from earlier feel less contradictory. Star formation and destruction are not opposing processes here. They are different expressions of the same gravitational system, operating at different scales and distances from the center. Phoenix A does not simply sit at the heart of the cluster. There is an old question that quietly haunts cosmology, one that sounds almost poetic when spoken aloud. Why is the universe filled with so much light? When its most powerful engines are made of darkness, stars shine, galaxies glow, clusters blaze across the electromagnetic spectrum. And yet, at the centers of many of these systems, sit objects that swallow light entirely. Phoenix A offers a direct answer to that contradiction. When matter begins its fall toward a black hole, it does not disappear quietly, long before it reaches the event horizon. Gravity tears energy from it with extraordinary efficiency. As gas spirals inward, it accelerates, compresses, heats, and twists magnetic fields into violent turbulence. In that process, mass is converted into radiation far more effectively than in any nuclear reaction inside a star. I remember the first time this fully settled in for me. The realization that black holes are not just sinks, but amplifiers. A spoonful of gas falling toward a black hole can release more energy than 1,000,000 nuclear detonations. Not because the black hole adds energy, but because gravity extracts it with ruthless precision. This is gravity turned inside out. In the Phoenix cluster, that conversion of matter into light happens on an immense scale. X-rays blaze from the cluster's core, tracing gas heated to tens of millions of degrees. Radio waves ripple outward, marking the paths of jets that erupted long ago. Infrared light reveals dense clouds collapsing into newborn stars, warmed by the very energy released from destruction nearby. None of this light comes from inside Phoenix A itself. The black hole remains invisible, a perfect absence at the center. Everything we see is a byproduct, matter struggling against gravity, losing energy step by step, radiating its final resistance before crossing a boundary from which no signal returns. There is something profoundly unsettling about that arrangement. The brightest regions are not signs of stability or comfort. They are warning flares, emitted by matter moments before annihilation. The universe, it seems, announces destruction with brilliance. Phoenix A makes that announcement impossible to ignore. The sheer luminosity of its surroundings rivals that of entire galaxies. Its accretion process floods the cluster with radiation powerful enough to reshape gas across millions of light years. The black hole's hunger becomes a broadcast, a continuous release of energy that alters everything nearby. What fascinates me is how little material is required to achieve this. Stars must burn enormous amounts of fuel over billions of years to shine. A black hole needs only a trickle of infalling matter to outshine them all. Gravity does not waste energy. It converts it with near-perfect efficiency. This efficiency is why black holes dominate cosmic evolution. They are not passive endpoints, quietly waiting at the centers of galaxies. They are engines, rare, extreme, and transformative. Phoenix A is not merely massive. It is active, persistent, and influential on scales that defy intuition. The Phoenix cluster glows because Phoenix A is feeding, yet this glow is not uniform or gentle. It carves structure into the cluster, leaving behind patterns that tell a story of repeated eruptions. Jets punch through surrounding plasma, inflating enormous cavities that remain visible long after the outbursts themselves have faded. These voids are not empty accidents. They are records of energy release, frozen into the shape of space. Each cavity is vast enough to swallow our Milky Way. Seeing that comparison always gives me pause. Entire galaxies reduced to reference units, used only to express the scale of something larger. It forces a quiet recalibration of perspective. As these cavities expand, they push hot gas outward, temporarily preventing it from cooling. Later, gravity draws that gas back inward. Cooling resumes. Matter condenses. Stars form. The energy cycle continues, driven by the same black hole that initially disrupted it. This is where the old dichotomy between destruction and creation begins to dissolve. Phoenix A does not choose one or the other. It enforces a rhythm in which both are inseparable. Collapse generates light. Light redistributes matter. Matter collapses again. I think this is one of the most difficult ideas to internalize, because it cuts against human intuition. We like clean categories. We label processes as constructive or destructive, good or bad, creative or terminal. The universe does not seem to share that preference. In Phoenix A, annihilation is productive. Consumption leads to illumination. Darkness powers light. This reframing matters because it changes how we interpret cosmic history. The brightness of the universe is not an accident layered on top of gravity. It is a direct consequence of gravity operating at scale. Black holes are not interruptions in the story of structure. They are central chapters. The Phoenix cluster becomes a case study in that truth. Its brilliance is not a sign of youth or excess alone, but of gravitational work being done. Energy flows outward from the core, shaping temperature, density, and motion across the cluster. Every photon carries information about that work. Those photons travel for nearly 6 billion years before reaching us. When they arrive, they are ancient, carrying memories from a universe half its current age. We intercept them briefly, extract their message, and then let them vanish into detectors. I sometimes think about that delay, how what we call now is always a reconstruction of the past. Phoenix A may already be different. Its feeding rate may have changed. Its jets may have quieted or intensified. But the light we see locks us into a particular moment, forcing patience and humility. Even so, the patterns are unmistakable. Phoenix A radiates with a consistency that speaks to long-term activity. This is not a brief flare or a dying gasp. It is sustained power, maintained over cosmic time. That endurance raises uncomfortable questions. If black holes like Phoenix A can remain active for so long, shaping their environments so profoundly, then how many features of the universe are consequences of processes we have barely begun to understand? How much of what we attribute to galaxy formation is actually black hole physics written large? The answer, increasingly, appears to be a great deal. Phoenix A demonstrates that the universe's brightest phenomena often emerge from its darkest mechanisms. Light is not the opposite of collapse. It is the signature collapse leaves behind. Energy released at the edge of disappearance becomes the very thing that allows us to see. Yet even with all this illumination, there remains a hard limit. We never see the black hole itself. No telescope, no wavelength, no clever trick allows us to peer past the event horizon. The singularity remains hidden, not by distance, but by principle. That boundary matters. Everything we infer about Phoenix A comes from its influence, not its interior. We study gravity by watching how it bends paths, how it heats gas, how it sculpts light. The center itself stays silent. There is a certain honesty in that silence. It reminds us that knowledge in cosmology is always indirect. We do not observe reality raw. We observe its consequences, its shadows, its distortions. Phoenix A is not seen. It is deduced. I find that oddly comforting. Science advances not by eliminating mystery, but by learning how to ask precise questions of it. Phoenix A does not answer those questions outright. It forces better ones. It challenges assumptions about growth, feedback, and the role of darkness in a luminous universe. At this stage, the story naturally slows. The more extreme the object, the closer we come to the edge of what observation can offer. Beyond this point, progress depends less on new images and more on interpretation, theory, and restraint. Phoenix A shines because gravity is doing work. But what happens beyond that shine, inside the horizon, near the singularity, remains untouched by light. And that unseen interior is where the next tension lies, waiting for us to confront not brightness, but ignorance itself. For all its size and influence, Phoenix A is never truly seen. No telescope has ever captured its surface, because there is no surface to capture. No image shows its core, because the core does not emit light. Everything we claim to know about it comes indirectly, inferred from the way its gravity rearranges the universe around it. This is an uncomfortable truth that often gets lost beneath the poetry of discovery. When astronomers speak of Phoenix A, they are not pointing to an object in the traditional sense. They are pointing to patterns, distorted orbits, heated gas, missing matter, jets carved into plasma. The black hole itself remains absent, defined more by what it removes than by what it shows. I sometimes think of it like studying wind by watching grass bend. You never see the wind itself, only the choreography it imposes on everything else. Phoenix A is similar. Its gravity leaves fingerprints everywhere, but the hand itself stays hidden. This indirectness is not a flaw of technology. It is a fundamental limit imposed by physics. The event horizon marks a boundary beyond which information cannot return. Light cannot climb out. Signals cannot escape. No matter how advanced our instruments become, that boundary remains intact. Outside the horizon, physics behaves in ways we can model, test, and refine. Matter follows curved paths. Energy heats and radiates. Time stretches and slows. Inside the horizon, those familiar concepts lose coherence. Our equations diverge. Predictions become meaningless. The singularity at the center of Phoenix A is not just unseen, it may be unknowable. Density approaches infinity. Spacetime curvature becomes extreme. The distinction between past and future collapses. General relativity, our best theory of gravity, ceases to function there. This is where humility enters science. We often speak as though every mystery is simply a problem waiting for better data. Phoenix A reminds us that some barriers are structural, not technical. The universe has places it does not allow us to look into directly. And yet, science proceeds anyway. By measuring the motion of gas, astronomers calculate mass. By analyzing radiation, they infer temperature and density. By mapping cavities and jets, they reconstruct histories of outbursts millions of years old. Each inference tightens constraints, narrowing what Phoenix A can be, even if it never reveals what it is. This approach requires a particular mindset, one that accepts incomplete access as a working condition rather than a failure. We build knowledge not from direct inspection, but from consistency across consequences. If gravity behaves this way here, and light responds that way there, then something massive and compact must be present. Phoenix A is a conclusion drawn from coherence. I find that deeply reassuring. It suggests that understanding does not require omniscience. It requires patience, cross-checking, and the willingness to accept that some truths arrive sideways rather than head-on. Still, there is a lingering tension. The closer we get to singularities, the more strained our theories become. Quantum mechanics governs the small. General relativity governs the large. Inside a black hole, both are relevant and incompatible. Phoenix A sits precisely at that fracture line. We speak confidently about accretion disks, jets, and event horizons. These are regions where our models still hold, but the heart of the black hole remains theoretical territory, a place where language becomes metaphor and mathematics becomes speculation. That gap is not a minor inconvenience. It signals an unfinished foundation in physics. A universe that allows objects like Phoenix A to exist must have rules deeper than the ones we currently know. This realization reshapes the role of black holes. They are not merely extreme objects to catalog, they are stress tests for reality itself. Each one asks whether our understanding of space, time, and energy is complete. And so far, the answer appears to be no. Phoenix A does not break physics. It exposes its seams. The more massive the black hole, the clearer this becomes. Subtle discrepancies in growth rates, feedback behavior, and environmental interaction hint at missing pieces. Phoenix A amplifies those discrepancies to a scale that can no longer be ignored, and yet, there is restraint in how science responds. Rather than inventing explanations recklessly, astronomers collect better data, refine simulations, and accept uncertainty as part of progress. Phoenix A is allowed to remain strange. I admire that restraint. It contrasts sharply with the human impulse to force closure. There is a maturity in admitting that some answers are provisional, some questions premature. The distance to Phoenix A reinforces that lesson. Its light began its journey before Earth had continents as we know them. By the time it reaches us, entire histories have unfolded and vanished. The black hole we infer today may already be evolving beyond our snapshot. This temporal gap adds another layer of humility. We are not observing a live feed. We are reconstructing a memory. Phoenix A exists now in a state we cannot yet know. Even so, the act of reconstruction matters. Each inference strengthens a framework that can be applied elsewhere. Phoenix A becomes not just a curiosity, but a benchmark, a reference point for testing how extreme gravity behaves across the universe. Through it, we learn how far our theories stretch before they snap. There is also something quietly profound about the idea that the most massive objects in the universe are also the most private. Stars broadcast their interiors through light. Galaxies announce themselves in color and motion. Black holes reveal themselves only reluctantly, through indirect whispers. Phoenix A embodies that restraint. It dominates its environment without ever introducing itself. Its presence is undeniable, yet perpetually incomplete. I think that tension is part of its power. It resists domestication by understanding. It refuses to become familiar, no matter how often we model it. And perhaps that is appropriate. Objects that bend spacetime itself should not be easily summarized. They should leave us uneasy, aware that comprehension has limits. As we trace the influence of Phoenix A outward, through jets, cavities, star formation, and light, we are mapping the reach of gravity without ever touching its core. The black hole remains an absence around which structure organizes. In that sense, Phoenix A is less an object than a question, a persistent one, written into the architecture of the Phoenix cluster. And that question does not ask what Phoenix A is made of. Compared to Phoenix A, almost everything else in the universe is temporary. Stars feel ancient to us because they live for billions of years, but on cosmic scales, they are brief flashes. Even galaxies, vast and enduring as they seem, are transitional structures. Gravity assembles them, evolution reshapes them, and time eventually pulls them apart. Phoenix A operates on a different clock. Long after the brightest galaxies in the Phoenix cluster fade, long after their stars exhaust their fuel and drift into darkness, the black hole at the center will remain. It will not shine. It will not announce itself. It will simply continue to exist, quietly exerting gravity on whatever matter still wanders nearby. I find this timescale difficult to sit with. Human history struggles to hold even a few thousand years in memory. Civilizations rise and fall faster than a single orbit of our galaxy. Against that backdrop, Phoenix A feels less like an object and more like a geological feature of spacetime itself. As the universe ages, star formation will slow, gas will thin. The easy fuel for both stars and black holes will become scarce. Clusters like Phoenix will grow dimmer, their brightest epochs already long past. Yet, Phoenix A will persist, feeding occasionally on stray gas, rogue planets, or the remnants of dead stars. Each meal will make it heavier, darker, and more dominant. In tens of trillions of years, when the last red dwarf stars finally flicker out, the universe will enter a long twilight. Light will be rare. Structure will be sparse. Most matter will exist as cold remnants drifting through expanding space. In that era, Phoenix A will still sit at the center of its cluster, a silent anchor holding what little remains. This is where black holes become the final repositories of structure. Gravity gathers matter, and black holes keep it. While everything else decays, they accumulate over unimaginable spans of time. The universe simplifies, leaving behind fewer and fewer objects capable of influencing their surroundings. Phoenix A is one of those survivors. Eventually, even black holes are not eternal. Quantum mechanics predicts a slow leakage of energy known as Hawking radiation. Particle by particle, black holes lose mass, evaporating over timescales so vast they dwarf all previous eras combined. For stellar mass black holes, this process already exceeds the current age of the universe by many orders of magnitude. For something as massive as Phoenix A, the timeline becomes almost absurd. Its evaporation time stretches beyond trillions upon trillions of years. Entire universes could rise and fall in the time it takes Phoenix A to lose a fraction of its mass. Civilizations could emerge, explore, and vanish without ever noticing a change. I think this is where imagination begins to fail in a productive way. Numbers stop helping. Language loses its grip. We are forced to accept that some processes unfold on scales that resist narrative entirely. When Phoenix A finally does evaporate, it will not explode. There will be no dramatic finale. The last whisper of radiation will fade quietly into the vacuum, returning energy to a universe already stretched thin and cold. Collapse will end not with violence, but with dissipation. What began as darkness will end as light, unimaginably faint. This ending carries a strange symmetry. Matter falls in, light comes out, over enough time. Even the darkest objects give everything back. Phoenix A is not an exception to entropy, only its most patient expression. I sometimes wonder what meaning has in a universe like that. When the last stars have burned, when the last black holes evaporate, when time itself loses the ability to mark change, what remains of stories, of observation, of curiosity? Perhaps that question misses the point. Phoenix A does not exist to be meaningful to us. It exists because gravity allows it. Our attempt to understand it is not a requirement of the universe, but a feature of our species. We look, measure, infer, and imagine, because that is what minds do when confronted with scales larger than themselves. In that sense, Phoenix A is not just an object at the end of time. It is a mirror held up to our limitations. It shows us how small our durations are, and how large our questions can still become. Even now, from nearly 6 billion light-years away, we detect it only as a smudge in data, a pattern in radiation. And yet, from that smear, we reconstruct a story that spans from the violent youth of the universe to its farthest future. That reconstruction is fragile. It depends on assumptions, models, and incomplete theories. But it is also remarkable. A creature whose ancestors once feared darkness now measures it across billions of years. Phoenix A will never know it was named. It will never care that we traced its jets, weighed its mass, or wondered about its fate. Gravity does not acknowledge observation, but we do. And in acknowledging Phoenix A, we place ourselves, briefly, humbly, within the same story of collapse, light, and time. From our vantage point, Phoenix A is almost nothing, a faint distortion in data, a smudge of X-rays, a pattern in radio waves that only exists once it has been processed, filtered, and translated into something our minds can recognize. If we stripped away the instruments, the equations, and the context, it would disappear entirely. And yet, from that near nothing, we build enormity. We know its mass not because we have weighed it, but because we have watched how everything else moves around it. Gas curves where it should not. Light brightens where it should fade. Entire regions of space seem hollowed out, shaped by forces that never show themselves directly. Phoenix A reveals itself through consequence, not presence. I find that deeply characteristic of the universe we inhabit. The most important things are rarely visible on their own. They announce themselves only through influence, through the quiet rearrangement of everything nearby. Gravity, time, entropy. None of them can be pointed to directly, yet all of them leave unmistakable traces. Phoenix A is gravity made legible. When astronomers first encountered evidence of something so massive at the heart of the Phoenix cluster, the instinct was caution. Numbers were checked. Models were rerun. Assumptions were questioned. This was not disbelief, but discipline. Extraordinary claims demand extraordinary coherence, not enthusiasm. What emerged from that process was not certainty, but confidence. The data did not collapse under scrutiny. It reinforced itself. Every independent measurement pointed toward the same conclusion. Something enormous, compact, and dominant sat at the center of that distant cluster. Calling it Phoenix A was an act of naming, but also an act of containment. Names allow us to hold ideas without being overwhelmed by them. Without a name, this object would remain an abstraction too large to comfortably think about. With one, it becomes a reference point. Distant, yes, but approachable in thought. I think about that often. How much of science is really about learning how to think at scales that evolution never prepared us for? Our intuitions were shaped by fire, water, and weather, not by space-time curvature or billion solar mass singularities. And yet, we stretch them anyway. We stretch them because the universe does not scale itself down for us. Phoenix A does not care that we struggle to imagine it. It does not care that our language fractures under the attempt. It exists regardless, exerting gravity, shaping matter, and radiating energy according to laws that operate without concern for comprehension. And still, we look. There is something quietly defiant in that. A refusal to accept that distance or scale should exclude curiosity. 6 billion light years might as well be infinity in practical terms. Yet we insist on reconstructing what lies there anyway. That insistence is not driven by usefulness. Phoenix A offers no immediate application, no technology, no survival advantage. It does not solve a problem we needed solved. It simply exists as a challenge to understanding, and that is enough. When I think about the effort required to detect it, telescopes orbiting Earth, arrays spanning continents, years of observation and analysis, it feels disproportionate to the faint signal received. So much work for so little light. But perhaps that imbalance is the point. The universe does not reveal itself generously. It offers hints, not answers. It provides fragments, not narratives. Phoenix A is one such fragment, forcing us to assemble a story from incomplete pieces. And, in doing so, it exposes the collaborative nature of knowledge. No single observer discovered Phoenix A. No lone mind could have traced its jets, weighed its mass, or mapped its cavities. Understanding emerges here as a collective act, distributed across instruments, institutions, and generations. That feels important to acknowledge. We often celebrate discovery as a moment, but Phoenix A reminds us that discovery is a process, a slow convergence of evidence, theory, and restraint. The willingness to wait years for confirmation, the willingness to accept that some aspects will remain unresolved. Even now, Phoenix A resists closure. Its formation remains uncertain. Its future is inferred rather than observed. Its interior is permanently hidden. We know enough to be confident, but not enough to be satisfied. I think that tension is healthy. It prevents black holes from becoming mere curiosities, neatly categorized and mentally shelved. Phoenix A remains active in our thinking precisely because it refuses to settle. It keeps pressing against the edges of our models, forcing revisions rather than confirmations. And in that sense, it functions as a teacher, not because it provides lessons, but because it reveals limitations. It shows us where our understanding thins out, where confidence gives way to humility. The largest black hole we know does not make us feel powerful. It makes us careful. That care extends beyond astrophysics. Phoenix A is a reminder that the universe is not obligated to align with our expectations. Theories are tools, not truths. Models are approximations, not mirrors. Reality remains larger than the frameworks we build to describe it. Standing with that realization can feel unsettling. There is comfort in mastery, in the sense that the world is explainable and contained. Phoenix A dissolves that comfort gently but firmly. It does not introduce chaos. It introduces scale. Scale changes everything. At small scales, certainty feels attainable. At large scales, certainty becomes statistical, provisional, and conditional. Phoenix A exists at a scale where even our best theories must be held lightly. And yet, this does not diminish the achievement of understanding it at all. On the contrary, it makes that achievement more remarkable. To infer the existence of something so massive, so distant, and so inaccessible is no small feat. It speaks to a particular kind of intelligence, one that does not require proximity to function, one that can operate through inference, abstraction, and patience. Phoenix A is not evidence of human dominance over nature. It is evidence of alignment with it. We learned how gravity behaves. We learned how matter radiates when accelerated. We learned how light travels through expanding space. And by letting those pieces interact, Phoenix A revealed itself. That revelation did not require us to go there. It required us to listen carefully to what the universe was already doing. I find that deeply grounding. In a time when speed and immediacy dominate attention, Phoenix A represents the opposite. Slow signals, ancient light, delayed understanding. Knowledge earned not through urgency, but through endurance. 6 billion years ago, matter fell toward Phoenix A and released energy. That energy crossed the universe patiently, indifferent to whether anyone would ever notice. Only recently did it encounter a species capable of interpreting it. That encounter was not guaranteed. It was contingent, fragile, which makes it meaningful in a quiet way. Phoenix A does not validate us. It does not exist for our sake. But our ability to notice it says something about what we have become. A species capable of asking questions far larger than itself, and patient enough to accept incomplete answers. This act of noticing does not end the story. It deepens it. Phoenix A remains where it is, continuing its slow work of gravity and radiation. We remain where we are, continuing our slow work of understanding. The distance between those two positions is vast, but not empty. It is filled with light, time, and inference. Phoenix A is so far away that it should feel abstract, like a line in a catalog rather than a thing. Even its distance sounds like a concept more than a location, because 8 billion light years is not a journey anyone can picture honestly. The mind tries to compress it into something manageable, and in doing so, it risks turning the real into a symbol. Still, the distance is part of the story, not a footnote. It shapes the way we know Phoenix A, and it shapes what kind of knowing is possible. The truth is, Phoenix A reaches us only as a faint smear on a detector. It arrives as a pattern in data, a statistical signature that becomes meaningful only after we impose structure on it. This is not a weakness of science, but a feature of working at cosmic scale. The universe rarely hands us objects, it hands us consequences. Phoenix A is recognized through its appetite and its influence, not through a direct look at its body. I think that's why the act of naming matters more than people admit. Phoenix A is not just a label. It's a way of making something impossibly large feel speakable. Without a name, it would remain a blur that only specialists could tolerate for long. With a name, it becomes something you can hold in your mind, return to, and build a story around. The name doesn't shrink the object, but it makes the gap between us and it feel crossable in thought. No probe will ever visit Phoenix A. No spacecraft will coast toward its event horizon and send back pictures from the edge. No human eyes will see it as anything other than a reconstruction assembled from signals. That limitation is not tragic. It's simply the scale of reality. The universe is full of places that remain unreachable by travel, yet reachable by inference. Phoenix A belongs to that category, and in a strange way, that makes it more instructive. One of the most quietly impressive parts of this story is how we piece it together anyway. Dishes on desert plains capture radio waves that have crossed the universe. Space telescopes register X-rays that left their source before Earth looked anything like it does now. Infrared instruments trace star formation occurring near a darkness that cannot be seen. All of that becomes a single narrative only because we learned how to translate faint signals into structure. A species that once feared the dark now measures it. And that shift feels like one of the more understated transformations in our history. Phoenix A also makes it hard to pretend we are separate from the universe we study. The distance makes it tempting to treat it as out there, as a spectacle beyond our lives. Yet the physics is continuous. The same gravity shaping galaxies in the Phoenix cluster shapes the air resting over your city tonight, the ocean tides, the slow drift of continents. The same atoms that spiral into accretion disks also make up your bones, your blood, and every object you've ever touched. The cosmos is not a stage we watch from safety. It is the substance we are made of. That idea lands differently when you sit with it for a moment. Phoenix A is not simply a monster we discovered. It is a future that matter can drift toward. It will outlast stars. It will keep feeding as long as anything wanders close enough to be claimed by gravity. In the long view, the material that makes us will not stay where it is. It will disperse, cool, scatter, and eventually become part of other systems, pulled into other wells of gravity, perhaps even wells like Phoenix A. Thinking that way doesn't make life smaller, it makes it less isolated. Somewhere behind the stars we can see, far beyond the reach of the naked eye. Phoenix A waits. It doesn't wait with intention. Of course, it neither knows nor cares that it has been found. That indifference is part of what gives the discovery its weight. We don't find meaning because the universe grants it. We find meaning because we insist on asking questions anyway. In a sense, Phoenix A is a reminder that curiosity does not require permission. The constellation Phoenix becomes a small anchor for the imagination here. You can stand under a night sky and look toward those stars, knowing that what you're seeing is not the black hole itself, not even the cluster that contains it, but a direction, a pointing gesture across distances so vast that language feels thin. Behind that direction lies something enormous, sculpting its environment, launching jets, carving cavities, feeding, and radiating. The mind can't hold all of it at once, but it can hold the fact that it is real. I think that's why the phrase, "a smudge on a detector," matters in this story. It sounds almost dismissive, but it isn't. A smudge is enough when the smudge carries structure, when it repeats consistently, when it aligns with theory across wavelengths and instruments. A smudge becomes evidence, then inference, then understanding. Phoenix A is reconstructed from something fragile, and the fragility is part of the beauty. We are not drowning in information, we are building clarity from scarcity. Every photon we catch from that distant cluster is ancient. It began its journey long before our species existed, long before our earliest stories, long before any human eye ever looked up and tried to name the stars. It traveled for billions of years through expanding space, indifferent to whether it would ever matter to anyone. Then, it ended its journey in a lens, in a detector, in a chain of circuitry, becoming a number that someone would interpret. That is an almost absurd path for information to take, and yet it happens constantly, quietly, across the night. There's a kind of humility hidden in that. We like to imagine the universe as something we are steadily conquering, one discovery at a time. Phoenix A suggests a different framing. The universe is not being conquered, it is being listened to. We catch what it gives. We work with what we can infer, and we accept that certain parts will remain forever beyond direct access. Understanding becomes less about control and more about relationship. That relationship is built on patience. Phoenix A is 6 billion light years away, which means its story arrives slowly, delayed, and incomplete. Even the most dramatic outburst, the fiercest jet, the brightest flare, becomes a quiet message by the time it reaches us. The universe speaks in ancient light, and we respond with mathematics. The exchange is never immediate, but it is still real. It's hard not to respect a cosmos that communicates on such a time scale. Phoenix A also teaches a simpler lesson that I keep coming back to. The universe is not built for our comfort. It does not arrange itself to be easily understood. It does not keep its extremes close, or its mechanisms visible. It builds its brightest phenomena beside its deepest shadows, and it lets those contrasts coexist. That doesn't feel cruel, it feels honest. The universe is not designed to reassure, it is designed to be what it is. In that sense, Phoenix A becomes more than a record holder. It becomes a boundary marker for comprehension. It shows us a place where our categories begin to fail. Supermassive becomes inadequate. Black hole becomes too small a phrase. Distance becomes more like time than space. We can still speak about it, still model it, still infer its behavior, but we do so knowing we are working at the edges. That awareness is not weakness, it's accuracy. Even so, the discovery enlarges us. We will never touch Phoenix A, but we can hold it in mind. We can locate it, describe it, infer its influence, and imagine its future. That act of imagining is not fantasy. It is disciplined inference extended by curiosity. When we name something like Phoenix A, we build a bridge across impossibility. The bridge is made of data and thought, not steel, but it still connects. The story ends, for now, with the simplest realization: there is more. More gravity, more mystery, more structures hidden in the dark, waiting not for us specifically, but waiting in the sense that they exist, and we may someday notice them. Phoenix A is one of the greatest teachers precisely because it does not teach gently. It reminds us that the universe is stranger than we can yet know, and still coherent enough to be studied. Nothing about Phoenix A asks to be resolved neatly. It exists whether we understand it fully or not, continuing its slow work at the center of a distant cluster, indifferent to observation. What we carry away is not an answer, but a sense of proportion, a reminder that even the darkest places leave traces, and even the faintest signals can tell enormous stories when we learn how to listen. The universe keeps going. So does our curiosity. This journey rests here for now,